begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. And we thank you that you love us first, independent of who we are, what we've done. Thank you that your righteousness can be our righteousness if we just accept your grace, Lord. And I pray you'd bless this class, help us to glorify you at what we do this day, Lord. In your name I pray. Amen. All right, so I started to tell you guys what systems of differential equations look like last time, right? So today we're going to talk about how to solve dx dt equals to, actually, let's, instead of using x, let's use a v here. dv dt equals to a times v, where a is constant, n by n matrix. All right. So that's sort of the big topic for today, is how do you solve problems like that. I showed you last time, well, this is a homogeneous system of differential equations. So once we learn how to solve that, then we can go and solve the non-homogeneous problem. Now, so what's this like? So how about this? If we try to solve dy dt equal to a times y, what do we solve that with? I once asked a linear algebra class, the math major linear algebra class, this, like 40 people, and no one could answer it. Or like, it would have taken them time to answer it. This was very troubling to me because like this is one of the things you guys just sort of like know from Calculus 2. Anybody who's getting a degree in math, science, engineering, something like that should be familiar with this differential equation. It's exponential growth, right? I mean, it says the rate of change of y is proportional to y itself. Of course, you guys can separate and integrate and all that good stuff, or you could look at this at the moment as y prime minus ay equals to 0, right? So you guys already know the answer here. Y equals to c1 e to the at, right? So we know that maybe an exponential should be involved in the solution, right? So what we'll do, so there's sort of, from this, there's sort of two natural paths, I think, if you think about it. And we'll follow each of these paths in due time. The first path we're going to follow is to say, oh, okay, well then maybe we can say v equal to e to the, well, a is a matrix, so that's kind of, what does that mean? I don't know. So let's say a to the lambda t times perhaps some vector u. I mean, maybe that'll work. Maybe we can construct a solution like that. It's kind of sort of like the exponential, right? So this is what's called an eigensolution. The other much more greedy, more adventurous route is to say, so should e to the, a times t be the solution? That would be the second more adventurous route to me, but that begs some questions, right? I mean, that's the most natural analogy to what we've already know from the case of just one differential equation with a constant, right? The exponential is the solution. So shouldn't it be just e to the, if a is a constant matrix, shouldn't it just be e to the at is the solution? But what does that mean? How do you take the exponential of a matrix, right? Does that even make sense? Right. Well, I don't want to say more about that at the moment, but we'll come back to the second route. So mostly we're focused today on the first case, all right? Now, so if it's going to be a solution, e to the lambda t times u is solution to dv dt equals to AV. What's that mean? We need that the derivative with respect to time of e to the lambda t times u is equal to a times e to the lambda t times u, right? In other words, if we plug the solution into the differential equation, it'd better work. You guys agree? Okay. Now, I told you briefly, now here we're assuming that u is constant, right? So if u is constant, that means we can pull it outside the differentiation, right? So I can just basically do this. U is outside the derivative, okay? Now what's the derivative of e to the lambda t? Well, it's lambda e to the lambda t. And then that u just rides along. On the other side, of course, we still have a e to the lambda t times u. Now what? E to the lambda t is on both sides. It's a scalar. We can pull it out. We can cancel it. So cancel the e to the lambda t, like so. And so what we get is that lambda u is equal to au. Definition. If there is non-zero u such that au equals to lambda u, then u is an eigenvector of A with eigenvalue rather lambda. Equivalently, there exists u not equal to 0 such that A minus lambda times the identity matrix times u is equal to 0. Here, this is the identity matrix. So like it could be 1, 0, 0, 1 for the 2 by 2 case. For the 3 by 3 case, 1, 0, 0, 0, 1, 0, 0, 0, 1, etc. The identity matrix is such that everything's in at 0, except for the diagonal entries, which are all 1. And the identity matrix is special. It has the following the identity matrix has this. It has I times A, well, let's say I times M is equal to M times I. It's equal to M again. You multiply any matrix by the identity matrix of the appropriate size, you just get back the matrix again. The identity matrix behaves like the number 1 for matrix multiplication, right? So if you don't see what's in red, I can go through the steps since we're starting here. So like AU, so here we go. AU equals to lambda u implies that's the same as AU minus lambda u equals to 0, right? And then this is the same as A minus, AU minus lambda, the identity matrix times u, because the identity matrix times anything is just that anything again. So like IU is equal to u again, and then I can factor out the u. Okay, so I'm just trying to give you the details of why what I wrote in red is equivalent to what I wrote in black there. So, apparently, what this little derivation shows us is if we can find eigenvectors for the matrix A, then we find solutions to the system, right? So to solve this equation, let me call it star, all right? So if we find u not equal to 0, solving A minus lambda I u equals to 0, then V equals to e to the lambda tu solves dv dt equals to AV. So this is a theorem. And such a solution is called an eigensolution. Okay? All right, so let's pick at this. Let's pick at this equation, a minus lambda I So if we have a minus lambda I times u equals to 0, right? What would happen? Let's call this matrix. Well, let's suppose that there was a minus lambda I inverse matrix. What would the inverse matrix times this? If the inverse existed, what would that do for us? Any inverse matrix times the matrix gives us back, by definition, the identity matrix again, right? Any matrix times the 0 matrix gives us 0 again. So if the inverse existed, then we would have IU equal to 0, which would shortly, we would quickly get that if the inverse matrix of a minus lambda I existed, it would force u to be 0. But what do we need u to be? We need u to be non-zero, right? Because if u is 0, then we're just getting the stupid solution to star, right? I mean, the stupid solution in the sense, is 0, like v equals to 0, does it solve star? Certainly. If we take the identically 0 function, we differentiate, we get 0. If we take a times 0, we get 0. So 0 equals 0. It works. Hooray, but it's useless, right? Unless all your initial conditions are 0, and then that's the solution. But that's not what we want, right? So what's this say? This is a contradiction, right? Contradiction to u not equal to 0. So that tells us that a minus lambda I is not invertible. Welcome. Do you go upstairs? Yeah, sorry about that. Just to recap, we're solving systems today, and we just figured out if we guess the solution looks like this, then plugging into the differential equation gives us this condition, lambda u equals to AU. That makes u if u is non-zero and solves this condition right here. It's called an eigenvector with eigenvalue lambda. And right now I'm working on deriving how we figure out what lambda should be. See, there's two moving pieces in our template, in our guess, basically. This is, of course, what is this? Where is this coming from? Is this derived? No. This is an educated guess, right? But this educated guess has two moving pieces to start with. It's got lambda and it's got u, right? So we need to pin down both of these as best as we can to figure out which solutions we're looking for. We just figured out that whatever this lambda is, it makes a minus lambda I to be not invertible. What equation can we write down then? If a minus lambda I is not invertible, what's that say? How about this? The determinant of a minus lambda I is equal to 0. So this right here, guys, is the golden ticket. This is the characteristic equation. This tells us, in fact, characterizes what the eigenvalues are for a given matrix. It turns out complex eigenvalues make sense for us too. Those come with a little bit more fine print. We'll get to that eventually. But like, what is this characteristic equation? Here, let's look at an example. I'll give you an example. Oh. Where is that thing? something. Ah. Aha. All right. So we could have a equals to 2 minus 3, 1 minus 2, right? What system of differential equations would pick that up as its coefficient matrix? Like, in other words, we're solving like x prime equal to 2x minus 3y, and y prime equal to x minus 2y, right? We're solving that system of, we're thinking about how to solve that system of differential equations, all right? So what's the characteristic equation for this A? By the way, just a point of a warning about references. There are some books that would, instead of this, they would write the determinant of lambda I minus A. That's the same equation. The question is, where do you want to put the minus? The reason I put minus where I do is because then I just have minuses down the diagonal. Otherwise, I have to remember to put a minus sign on every entry in A. It's just more opportunities for sign errors. So I choose to work with that characteristic equation because I think it leads to less sign errors. It does lead to slightly weirder looking equations to start with, though. So the determinant of A minus lambda I, what is that? Well, that's the determinant of 2 minus 3, 1 minus 2, minus lambda times the identity matrix, which is 1, 0, 0, 1. I don't usually write down this step, okay? I'm writing this down once, but I will soon always jump to what I'm about to write, which is 2 minus lambda, minus 3, 1, minus 2 minus lambda. By the way, if you don't like lambda, you could use R. I think the text uses R instead of lambda. I will use lambda. It is my custom. All right, so the determinant, well, we already know how to do that. This is 2 minus lambda times minus 2 minus lambda plus 3. And then we got to multiply, right? I like to do this. That's lambda minus 2 times lambda plus 2. See, if there's a minus in both, I can just kind of multiply both by minus 1. It doesn't change anything. And I just do better algebraically when I do that. I don't know why, but I do. So this is lambda squared minus 2 lambda plus 2 lambda minus 4 plus 3. In other words, lambda squared minus 1, also known as lambda plus 1, times lambda minus 1, right? Factoring, of course, reveals zeros, right? So we either get lambda 1 equal to minus 1, or lambda 2 equals to 1. These are the eigenvalues for this matrix. All right? I'll keep working on this in a second, but before I do that, I just want to take a second to make an observation about the characteristic equation. Observation. The determinant of A minus lambda I is an nth order polynomial in the variable lambda. Now, if you don't like working with lambda, you could take lambda and replace it with t or something, but you got to make sure you don't. I mean, t is kind of a bad choice because t is time, perhaps, or the independent variable here. You know, you could use a different letter for lambda if you wanted to. If it helps you with the algebra, you could use x, but be careful not to confuse that with the different meaning of x that we also have here. But this is an nth order polynomial in the variable lambda. So the fundamental theorem of algebra says what? Do you guys know? Fundamental theorem of algebra, what does it say about an nth order polynomial equation if we're working over the complex numbers, how many solutions do we get? If it's got real coefficients, we get n solutions, right? Possibly complex, possibly repeated, but all of the complex solutions have to come in conjugate pairs, right? This fundamental theorem of algebra says if you've got an nth order polynomial equation, you get n solutions. Possibly complex, possibly repeated, but you get n solutions. So there definitely will be n, up to n, but not more than n eigenvalues for the matrix, all right? In this case, we found 2 distinct real eigenvalues for this A, right? If you got a 3 by 3 matrix, you can find at most 3 distinct eigenvalues, okay? You could find 1 real and 2 complex. They come in a conjugate pair, right? If you had a 5 by 5 matrix, you could have 5 distinct reals. You could have a repeated root 5 times. You could have a pair of complex roots, each a conjugate pair and 1 real root. I mean, these are the kinds of choices we have because it comes back to factoring. How can you factor an nth order polynomial? Either linear factors or irreducible factors. Irreducible factor gives us complex roots. The linear factors give us the real roots, possibly repeated in both cases, yeah. Now, so here's the, I should probably tell you, what's the big story here? I mean, the other lectures we've had, one of the things I've done for you guys is I've stated the existence and uniqueness theorem, right? We haven't covered that for systems yet, have we? No. What do you think, if you guys had to guess, what do you think the existence and uniqueness theorem is going to say for a system? If we have a linear system, right? Theorem, if we have dv dt equals to, let's say, I'll say PV plus F, where P and F are continuous on some connected subset of real numbers. What do you suspect? And here, this is n by n matrix of functions. Yeah. What do you think the existence and uniqueness theorem might look like for this system? Well, I'll just tell you. It says V is equal to the homogeneous part of the solution plus the particular part of the solution, where dVH dt is equal to PVH and dVP dt equals to PVP plus F. In other words, we have a particular non-homogeneous solution, and then there's a homogeneous solution. The general solution is a linear combination of those, all right, where VH is equal to C1x1 plus C2x2 plus, perhaps I should use V1s through, I'll use V1 and V2 here. Sorry, guys. It just occurred to me there's a good reason for doing that. Cn, Vn is formed from linearly independent V1, Vn. So I'm not being very precise in my language here. I'm sorry, guys. Let me try to summarize what I'm saying is, if you have such a problem, there exists a fundamental solution set. Again, we're going to be able to find n linearly independent homogeneous solutions. And again, the homogeneous piece of it is a linear combination of those fundamental solutions. And again, the general solution, if there isn't a homogeneous piece, we just need one particular solution. We take that and we add the linear combination of homogeneous solution. That gives us the general solution. Furthermore, if we had initial data, right? If V of, let's say, T sub naught was equal to V sub naught then there exists unique choice of C1, C2, Cn, for which V equals to VH plus VP solves the initial value problem. So what I'm trying to tell you is it's, in some sense, just like it was before. It's the same song and dance. We're still looking for n homogeneous solutions that are linearly independent. All right? And the theory is still very kind to us. If we have, continuous pieces to the differential equation, then the solution exists and it uniquely fits initial data. On all of I, too. It's really nice. All right, but this is just a backdrop. All right, so what I'm trying to tell you here is it looks like for this problem, since we found two eigenvalues, right? If we can find the corresponding vectors u1 and u2, then we'll have the general solution to this problem. See, because if it's going to turn out that the solutions corresponding to -1 and 1, they're going to be linearly independent. In fact, this is generally true. If we have distinct eigenvalues, the eigensolutions we get for distinct eigenvalues will be independent solutions. Just like it was in the scalar case, right? If you had different values for lambda, those didn't have like overlap. You didn't have to multiply by x, right? By the way, multiplication by x here, or in this case, multiplication by t, is not as simple as it was before. There's wrinkles. Okay, so let's finish this example 1. Let's actually finish the solution here, find the general solution. So we found the eigenvalues. So next step, we need to find u1 such that a minus lambda 1 I u1 equals to 0. All right? So there's sort of 3 steps here. Step 1 is to calculate the characteristic equation, find the eigenvalues. It is so important that you do this correctly. If you do this wrong, everything else you do past it's just complete nonsense. And if you go past this point and don't go back and fix it, I can tell you don't understand what you're doing too. It's not something you can do with half understanding. If you get those wrong, the algebra you do past this point does not make sense. So it's really important to do this correctly and to be aware that if the next step blows up in your face, that just shows you need to go back and look at your characteristic equation again and fix it. That's all. Okay, so this lambda 1 is -1, right? So this is actually a plus I. So I can go back to this right here. This matrix is a minus lambda I, right? So if I just put lambda equal to -1 in this matrix, that gives me what I should put there, which is 3 minus 3, 1 minus 1. And for u1, I'll use a u and a v just to have some disposable variables there. Okay. So can we solve this 2x2 system of equations, right? If you did this right, you cannot get distinct equations for the 2x2 case. Because if you got distinct equations, we'd be back to just crossing at the origin, which would be a unique solution of 0, which is not what we want. The eigenvector must be non-zero. But you see here, good news, right? The first row and the second row, they're the same silly equation, aren't they? So you can just pick whichever one you like. I like the second one. It says that u minus v is equal to 0, right? AKA u equals to v. So we can set v equals to 1, and that tells me that u1 equals to 1, 1 is my eigenvector with eigenvalue -1. If instead of setting v equals to 1, I had set v equals to like k, what would have happened? If I instead said, put this to be k here, it would just do what? It just puts the k over here because they're both going to be k. So you can pull the k out. In other words, any other choice of v gives me a constant multiple of 1, 1. So why use 1, 1? Because it's easy to write, right. And because at the end of the story, we're forming a linear combination of solutions, right? So you have this freedom to adjust the coefficients. That just, relabeling u1 just corresponds to relabeling c1, which is just a different way of indexing initial conditions. So there's really no harm, given our use of eigenvectors, of just picking a specific eigenvector. There's always going to be infinitely many of them. Because we're in the case the determinant's 0, there's always infinitely many solutions, right? We just need to pick one in this case. There's only one of these solutions that you're not allowed to pick. Which one? There's one thing I can't do. Yes, at v equal to 0. That is the one thing which is forbidden. Okay. Now, imagine you did this, you come to this equation, and you don't get the same equation repeated. You get two generally different equations. It forces you to be 0. What does that mean? That means that minus 1 wasn't really an eigenvalue. That means you got to go back here and you got to figure out where you made a mistake. That's all. Step 3 in this problem is to find, step 3, we need to find u2, solving a minus I times u2 equal to 0, right? This is what that looks like when lambda 2 equals to 1, right? So specifically, that is 1 minus 3. 1, yeah, minus 3. Okay, so this is kind of like in your face the same equation, right? I mean, it's kind of hard to miss. Yeah, that's the same equation. And so pick whichever one you like. This is u minus 3v equals to 0. So aka u is equal to 3v. So set v equals to 1. We get u equals to 3. And my eigenvector with eigenvalue 1, u2, is going to be 3, 1. So I found my eigenvalues, found my eigenvectors, and then step 4, let's put it all together, right? Assemble the pieces. Thus, the general solution is x. Oh, I'm sorry, I was using v, wasn't I? V equal to c1 e to the, what was it, minus t, and 1, 1, plus c2 e to the t, 3, 1. And there I'm of course, using the theorem that, well, we could prove. I mean, proof of these theorems is actually kind of interesting, and it basically is numerical methods. It involves an iterative procedure. It's actually kind of interesting, but I don't really know how to test on it, and I'm pretty sure there's enough in this course already. So, so there it is. This is what I would call the general vector solution to the problem. You see why I call it a vector solution? It's really not that complicated. It's because I wrote it as a vector. Now, what does this actually say if we go back to what I'm about to circle in blue? What are the scalar solutions here? What's the general scalar solution, if you will? So by default, guys, sorry, I've forgotten how to say guys. The scale, if I just say solve a system, I am content with the vector solution. I, in fact, prefer it. It's easier for me to grade. there's one less place for you to make a mistake in a silly way, like I would at the end of the problem. So if I want scalar solutions, I will ask for them. I could totally understand somebody else teaching this course and say that the problem's not done until you write what I'm about to write in blue. And I understand that. It's just, I like vectors. What can I tell you? So x is equal to c1 e to the minus t plus 3c2 e to the t, and y is equal to c1 e to the minus t plus c2 e to the t. It's easy enough to see what I did there. What did I do? I just read off the first and the second components of the vector solution, right? Those are respectively the x and y pieces. The interesting thing about the system, right? The x solution and the y solution, do the solutions exist on their lonesome? I mean, are they? No. I mean, look at how the c1 and the c2 appears in both the x and the y solutions. In other words, these solutions are sort of intertwined. I'm sorry, a technical term, intertwined, right? And this method of finding eigenvectors somehow untwists them and lets us solve it. There's a coordinate change going on here behind the scenes, truth be told. We don't need to do all that, though, because I gave you a complete derivation here. I mean, we don't have to talk about coordinate change if we don't want to. But any questions about this? Is the procedure clear enough? Step number 1, you look at the characteristic equation and find the eigenvalues. Step number 2, you find eigenvectors. For each eigenvalue, as many as you can. And that's step 2 and 3 for me. Step number 4, put it together, right? Now, when is this not going to work? You're like, it always works. We're done for today. Good job. No, not quite so simple. Yeah. Here, let's look at another example for a little bit more. It turns out there's a lot of things that can happen for a matrix. It may or may not be the case you actually have enough eigenvectors to make all the eigensolutions you need. All right? So it so happens, I think you guys, even if I hadn't written this down, if I had just proceeded today without ever writing this, probably you still would have understood. Because what we're doing is exactly like what we have been doing. But again, I mean, technically it's a new arc of the theory because it's a system. It's not just a single equation. But what is it?
We were working in the library the weekend, and they just put whiteboard over the drywall, so it was all bumpy and really hard to erase. So I was noticing how easy it was to erase these plain whiteboards.
They put, what did they do?
They just like painted the sheetrock.
Oh, so they haven't.
So it's like not a flat, like smooth surface like that on the wall.
So our nice whiteboardy roomed library study rooms are now bumpy? Or they always been bumpy? Oh. Shit, I've spent a lot of time in those rooms, so I know, but no, not really. I don't know, you can get the smooth white stuff from Home Depot for like, it's like 15 for a 4x8 sheet. That's what I have in my office. Of course, I put in a work order to have the right people install it, you know. Actually, vandals broke into my office and installed it one weekend. But in my brother's school, there's a professor who had vandals break in one week and tear out his carpet and put in hardwood floor, which is really convenient for him because he has an allergy. But vandals will do things. Let's see here. So another example. This one will have a little bit different. This will start to illustrate some of the subtlety here, okay? And also how it's as much as it's like what we did before, it's also there's new features here you got to be aware of. So we could try to solve the system. This would correspond to what? This would, aka x prime is y plus z, y prime is x plus z, and z prime is x plus y. This system has that matrix, right? All right, so we got to calculate the characteristic equation. So we have minus lambda, 1, 1, 1, minus lambda, 1, 1, 1, minus lambda. So this is the determinant of a minus lambda I. And I mean, 3 by 3 determinants are just a pain. There's no getting around it. I mean, there is. I know the answer. But let's see here. But let me not do that. All right, so I'll show you. Minus lambda, 1 minus lambda, minus the determinant of 1 minus lambda, and then plus the determinant of 1 minus lambda 1. Is anything the same here? Oh, these are actually the same, except that the rows are flipped. So we'll actually just get 2 copies of that. But I'll just write it out. So this is minus lambda times lambda squared minus 1 plus, well, I'll just get straight to it. 2 times 1 plus lambda. You'll confirm that, right? Factoring by grouping for the win here, guys. This is minus lambda times lambda plus 1 times lambda minus 1 plus 2 times lambda plus 1. Well, we got the same factor in 2 terms. Hooray! So, see here and here, yeah. So we can factor that out. And that leaves me what? That leaves me minus lambda times lambda minus 1 plus 2, which is quadratic, which means it can't escape our methods, right? I'll pull a minus out because I find it nice. Lambda plus 1. So that gives me a lambda squared plus lambda. Oh, I'm sorry, minus lambda. Minus 2. So that's what? This factors into what? Lambda plus 1 times lambda minus 2, yeah? So I have lambda plus 1 squared times lambda minus 2. So we have, what we say here is we have lambda 1 equals to minus 1 with algebraic multiplicity algebraic multiplicity 2. In other words, minus 1's repeated, right? The reason I say algebraic is because there's something called geometric multiplicity, and they don't have to match up. When they match up, it's most simple. When the algebraic multiplicity matches the geometric multiplicity, that means that we have enough eigenvectors, and we cannot pursue the second crazy purple path of the matrix exponential. But let's see here. I'm not sure what's going to happen with this one. I kind of think that this is going to have enough eigenvectors, right? Let's find out here shortly. So we good? So far, so good? All right. Let's find those eigenvectors. Which one do you guys want to do first? I think 2 is the easy one, right? Let's do 2 to start with. So 2 should be more or less just like what we've already done. Lambda, I guess I'll call it lambda 2, since I did call it. Lambda 2 equals to 2. I have to solve a minus 2i times, let's say, u. I'm going to call it, I don't know, whatever. I guess I'll call it u1 for lack of imagination. That's awkward. I'm going to call it u3 for reasons that will become clear as we go on here. What's that? Oh, yeah, sorry, my 2's and my lambdas. I mean, technically my lambdas are all wrong. Like, lambda's actually this, right? True. I started writing lambda the wrong way a long time ago. I no longer have the ability to change that. So it's, I don't know, it's kind of like voting Democrat or something, I guess. I don't know. Seems good at the start, but at some point you realize it's a mistake. Probably could say the same about Republicans, though. I don't know. Let's see here. Let's see here. Oh, okay. So what do we got? A minus 2i is, it's actually, I have to subtract 2 from the diagonal, which is, okay, so it's really simple. This is minus 2, 1, 1, 1, minus 2, 1, 1, 1, minus 2. That's what happens when I subtract 2 off the identity, right? And now here, I have disposable variables u, v, w. All right. Yeah, this one's a pain. Man. See, it's not at all obvious. See, here's where you can get into trouble, right? Because it's not obvious that these are the same equations or that they're related. Do you guys see how these 3 equations are related? I don't see it right off. Sometimes when I'm faced with a problem like this, I'll go back to the original matrix and just ask myself the question, can I find some vector that when I multiply by this matrix, I get back twice the vector again? You know? I think if we do 1, 1, 1, it'll work. So I'm trying to say this seems unfun. I guess. U3 equals to 1, 1, 1. Does that work? I mean, if you go back here and multiply this a times 1, 1, 1, what do you get? 1, 1, 1 times 1, 0, 1, 1 gives me 2. 1, 1, 1 times 1, 0, 1 gives me 2. 1, 1, 1 times 1, 1, 0 gives me 2. So it's pretty easy to see that 1, 1, 1 multiplied by this matrix gives me back twice 1, 1, 1. So that is an eigenvector, right? Okay, so you're like, well, that's great that you can guess that, but what's the method to do this? Well, I showed you last time. It's the row reduction thing. It just would eat an inordinate amount of my time. I'll start it, but I'm not going to finish it. Although I will show you a website. So basically, my next move would be to clear out that. So I'd have like 0. I guess my first move would be is to move this up here. You can switch rows. Otherwise, I'm going to have to deal with fractions. I can't stand fractions. So I switched row 1 and row 2, and then I clear that 0 out, you know. So I added 2 times that, so that gives me minus 3. 3. I subtracted the first from this, so that gives me 3 and minus 3. Oh, fine. I guess it's not too bad. Is that a 1 or a 7? Not 1. It's okay. All right, so speeding it along here, this gives me 1, minus 2, 1, 0. After a few steps, I get this, all right? And then that gives me which basically tells me that u is equal to w and that v is equal to w. So you set w equals to 1, and that gives you u3 is 1, 1, 1. Right? But you know, when you can guess and check, it is faster. Right? A lot of these book problems that I'm giving you, you might be able to guess if you get stuck on the algebra. Now this much, here's some fun guidance from linear algebra. Linear algebra tells us that if you have a eigenvalue with multiplicity k, there can be at most k eigenvectors. So like if I have 2 and there's just an eigenvalue of 2 and it's not repeated, that means I can get at most 1 independent eigenvector from this. In the case -1, we could have up to 2 eigenvectors, linearly independent from that. Let's see how that goes. So lambda 1 equals to -1. So we need to solve a plus I u equal to 0. And so what's that? Oh, I like this one more. 1, 1, 1, 1, 1, 1, 1, 1, 1. Okay, so it's pretty easy to see what the row, I mean, do you really need row reduction here? I would argue no. I mean, row reduction is a tool to reveal the true nature of a system of equations when it's not clear from the start. If it's clear what the system of equations is from the start, we don't need row reduction. Like the 2x2 system we did, example 1, we didn't need row reduction, right? This, we don't need row reduction. It's just the same equation repeated, right? So like all 3 of the equations just tell me what? They tell me u plus v plus w equal to 0. Now here's where you guys get into some trouble because this is kind of unfamiliar territory. But what this says then is that u is equal to, let's say, minus v minus w, v and w, right? So you can solve that u is equal to minus v minus w, right? That makes sense? And then we can, what we do is we pull out the v, and we got a -1, 1, 0. And pull out the w, and you got a -1, 0, 1. When you do this calculation, theory of linear algebra guarantees that the vectors which appear in this way will be linearly independent. They'll be distinct vectors. And those will give you distinct eigensolutions if they're there. Okay, so this vector we're going to call u1, and this vector we're going to call u2. And we just we're done. So thus x equals to c1 e to the, what was it, 2t, e to the 2t, 1, 1, 1, plus c2, what was my second eigenvalue? -1. E to the minus t, -1, 1, 0, plus c3, e to the minus t, -1, 0, 1. There you go. That, my friends, is the general solution to example. Oh, I forgot to number it. This is example 2, right? I think it's fair to say that covering 10 of these in a given day would be unkind to me and to you, right? But you do need to do a bunch of these before you really get used to them, right? Now, do you guys see something really, really different about this? What would have happened? Let's see if I can get back to it. Example 3. You guys, how would you solve d plus 1 squared times d minus 2 y equals to 0? What would the solution of that been? You guys know. We get what? We write it down. Y equals to c1 e to the minus t plus c2 what? T e to the minus t, right? Plus c3 e to the 2t. And there it is. We have to multiply by t in this scalar case because there's really no other avenue to gain linear independence of the solution. I mean, like here, this also has lambda equals to -1 twice and lambda equals to 2. But there, the use of lambda is quite different, isn't it? That's a different lambda. That's the characteristic equation for an nth order problem. This is the characteristic equation for a system of 3 first-order differential equations. These are related ideas, but they're different, right? In particular, the thing we did before test 1, or on test 1, you have to have the t when there's a repeated root. Like, there's just no way around it. Now that we have vectors in addition to just the e to the lambda t term, there's different ways to gain independence when there's a repeated root. There's no multiplication by t here, is there? I mean, notice this. You don't have to multiply by t when there's a repeated root for a system. Now, I'm not saying that there's never multiplication by t. There can be multiplication by t, but not for this example. Sometimes there is, sometimes there isn't. It turns out the question of when you do have to multiply by t is more complicated for systems. We're going to work our way to it. We're getting to it. But I think this is a good start. So you guys understand the method again? Just to reiterate, calculate the characteristic equation, find your eigenvalues, find as many eigenvectors as you can, and if you can find n distinct solutions, you're done. General solution. Game over. All right, so we'll take a 10-minute break here, and when we come back, we'll start again. And let's start at noon. We'll take a slightly longer break, and when we come back, I'll continue on with this, and hopefully we'll get into the complex case and some more examples.